Okay, we are doing a section that's not in your book, and the reason being is at the end of the year, you might be able to take a test that will give you credit for Calc 1, and this stuff is not in our book. So we are going to call this for 9-day 1, and it's all about related rates. And what related rates are, they happen when more than one dimension is changing with time being the key factor here. For example, if you continue to pump air into a balloon, what values are changing with time? So if you think about it, as the air goes in, the radius is going to grow, which is going to make the diameter grow, which is going to make the volume grow, which would make the surface area grow. Every dimension possible is going to grow with time because you continue to put air in. So what we're going to be doing is looking at the rate that any one of these are changing at a specific time. So it's a 4-step process. Take you through it. First thing you need to do is draw a picture. Label all of the dimensions that are changing with time with variables, not the numerical values given in the problem. That's key. Don't put any numbers in your picture unless they're constants. It's impossible for them to grow. Like say the length of a ladder, that's not going to grow or shrink with time, it's a constant. Okay, write an equation relating the variables. And if you don't remember, you may have to ask Google or Siri for some of the formulas from geometry if you've forgotten them. Then you're going to write the rate of change equation. Here's where calculus comes into play with respect to time, and it's a 2-step process. So you take the derivative of each term like you normally would using all your rules. After you do the derivative of each term, this is key. Multiply each term by the rate of change with respect to time. Be sure to use appropriate derivative notation for each term. So let me show you what I'm talking about here. Say our equation we wrote was y equals 2x to the 4th. So there are two variables here that are going to change with time. Y is going to change and so is x. So we do the derivative of y, which is 1. And then we have to multiply by the rate of change with respect to time. And all that is the derivative of y with respect to time. So dy over dt equals, now we do the derivative here, that's just going to be 8x cubed. Normal derivative, but now we've got to multiply by the change in x with respect to time. That would be dx dt. It's bad x. Okay, let's do a couple more just so you have it. Say we have the area for a circle. A equals x squared plus y squared. I've got 3 variables that are changing with time. So the derivative of a is a 1, and you always have to remember to multiply by the rate that a is changing with respect to time, dA dt. Do the x term, which will be 2x, multiplied by its rate with respect to time, dx dt. And then the y term, 2y, times its rate with respect to time. And then the last one that I want to do is, say we've got y equals z times x. Okay, I got 3 variables, but over here you've got a product rule. So you still have to remember all of your derivative rules. So derivative of y is 1 times dy dt. Over here I've got to follow the product rule. So that is, this is your u, this is your v. So I take the derivative of z, which is 1, times by its rate, because I'm doing the derivative here, dz dt, times by the v term, which is just x. I didn't do the derivative of x, I just took it, so moving on, plus, now the second part of the product rule says keep the u, so that's a z, times by the derivative of the second term, the derivative of x is 1, and then I got to do that rate of change with respect to time, which is dx dt. And it looks ugly, but they're okay. All right, so after you've got your rate of change equation, now is when you substitute the given values for the specific time into your rate of change equation, and solve. And you might have to use your original equation to find an unknown value first, because you're, say they give you the area and this x value, but you're going to need to know the y value to put it into your rate equation. So you might have to come back here and do a little algebra first before you can plug everything in. So we're just going to do some examples now. All right, so we'll go back to that first one that I talked about. It says air is being pumped into a balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius increasing when the diameter is 50? So they are giving me a rate here. This is a rate with respect to time. And how fast is the radius increasing? That's another rate. That's another derivative at a specific value. So draw the picture first. So we've just got a sphere. And we are talking about volume. So again, this is where you have to remember from geometry your formulas. If not, find a way to get it. But the volume of a sphere is 4/3 pi r cubed. Okay, so step one's done. The only two variables we're going to work with are radius and volume. So now I'm at step, I drew the picture, wrote the equation. Now I'm ready to write my rate of change equation. This is where I'm going to do derivative all the way through. So I'll start with the v. The derivative of v is 1 times by its rate with respect to time, dv dt, equals, remember 4/3 and pi are just constants. They're being multiplied, so they just carry along. The only thing I'm doing derivative of here is this r cubed. So the 3 comes down and gets multiplied by the 4/3. And then that'll be r squared times by its derivative with respect to time. You can't forget that. dr dt. Okay, now at this point, we've got to see what's given and substitute in. It says, so what we're looking for is how fast is the radius increasing when the diameter. So how fast is the radius increasing? That's our dr dt. So we are looking for dr dt. And what I know is this, that the volume increases at a rate of 100. This is dv dt. And I know that the diameter is 50. If I look back in my equation, I need to know dv dt. Got that. I need to know the radius. Well, if they give me diameter, I can get the radius at 25 feet. And then I am trying to solve for dr dt. So it just turns into a simple algebra problem. So 1 times anything, I don't have to worry about that. dv dt is the 100. Here I'm going to do a little simplifying. I'll have 4 pi Radius is 25. Gotta square that. And then dr dt is what I'm trying to solve for. Okay. Now it's just a little algebra. I'm going to work all of this out. I'm just going to divide by it. So it's going to be 100 divided by 4 pi. I don't have a calculator here, so I'm just going to make that times 25 times 25 equals dr dt. So let's see. 25 goes into 104 times 1. So I get 1 over 25 pi is my rate of change for the radius with respect to time. So then my units would be the radius dimension would be feet per, my time was in seconds, so feet per second. And I don't have a calculator handy to actually do this division to see what it is as a decimal, but we'll go with that. Oh, not feet, centimeters, sorry. Oh yeah, you guys are laughing right now, aren't you? Centimeters, centimeters, so centimeters per second. I don't know what I was looking at. Okay, try another one. Here we've got a 10-foot ladder rests along a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom is 6 feet from the wall? All right, picture first. So here's our wall, here's our ground, here's our 10-foot ladder, and then the bottom of this ladder is going to get pulled out, which means this horizontal distance is going to grow while this vertical distance is going to shrink. So both of these dimensions are going to change with time. The 10-foot ladder is going to stay 10-foot ladder. So this distance is going to change with time, and so is this distance. I'll call them two separate variables. There's my picture. My equation now that's going to relate all of this is just Pythagorean theorem. So the picture is going to tell you what your equation is going to be. The key is to not put in this 6. That's only at a specific time that's at 6. That's not saying that this is always going to be 6. So this changes. So don't put the 6 in. So our equation is going to be x squared plus y squared equals 10 squared. Okay, so after you've got your picture and your equation, now you do the rate equation with respect to time. And that's just do the derivative and multiply everything. Maybe I should call that the rate equation. So we'll do derivative here. It's 2x times by the derivative with respect to time, dx dt, plus, now this derivative is 2y times dy dt, and the derivative of 100 is 0. So now let's substitute and see what we're trying to solve for. So it says if the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So this is a derivative, it's a rate, and it's the rate that x is changing. So the dx dt is 1 foot per second. How fast is the top of the ladder sliding down? That's the change in y. So dy dt is what we're looking for. And I know that, let's see, is that all I need? Oh, I need x and y because I'm solving for this one. And I know that the bottom is 6.